we're going to talk about some special matrices that we encounter and some properties involving those. First, we're going to be looking at square matrices in which all the entries off the main diagonal are 0. Such matrices are called diagonal matrices. For any diagonal matrix, then, to be off the main diagonal means the row and column number are not equal. So the ijth entry of such matrices is 0 if I is not equal to j. So notice it's just all entries off the main diagonal are 0. That's the definition. These are all diagonal matrices. If I sort of block off, remember the main diagonal entries are going down at an angle from the top left to the bottom right, because this is location row 1 column 1 where the 9 is, and this is row 2 column 2 where the -6 is. So everything off the main diagonal is 0. Same thing in this one. Same thing here. This is the 0 matrix. It's actually diagonal. Remember, the definition is anything off the main diagonal is 0. It is indeed the case. It doesn't really matter what the diagonal entries are, though. They do not have to be non-zero. It doesn't say that in the definition. Of course, the identity matrix of any size n is, of course, also going to be diagonal. Of course, remember, this has to be a square matrix. In general, we can write diagonal matrices this way. And notice, we don't use a double subscript notation. There's really no need to, since there's only one entry per row, essentially, right? The entries along the main diagonal of any consequence. All the others we know are 0. Now, with diagonal matrices, these are the ones that behave very much like real numbers when we're dealing with when we're looking at operations. So, for instance, if we have an n by n diagonal matrix D, then it's going to be invertible if and only if all the entries along the main diagonal are non-zero. So only if these entries are non-zero will the matrix be diagonal, and it doesn't matter the size. If such a diagonal matrix is invertible, then its inverse is given here, which is simply what? The reciprocals of these main diagonal entries. So you see why it can't be 0 anywhere along the main diagonal, because if I take the reciprocal of 0, it's undefined. So, for example, if D is equal to this matrix here, then its inverse, well, first of all, I know it's invertible because both the diagonal entries are non-zero, and therefore its inverse is just going to be the reciprocal of those entries, right, corresponding in the corresponding locations. Reciprocal 4/5 is 5/4, zeros everywhere else. So these are indeed going to be D inverse is the inverse of D, and I can show that, for instance, if I multiply D times D inverse, just to compare what we're going to get here. Two by 2 times a 2 by 2 is going to, of course, give me a 2 by 2. First row multiplied by the first column. Notice the 3 and 1/3 give me 1, 0 and 0 give me 0, so adding that together gives me 1. Here, 3 0 times 0 5/4 gives me 0. 0 4/5 times 1/3 0 gives me 0. 0 4/5 times 0 5/4 gives me 1. And so we clearly see that that's the case. And if you change the order, we're going to get, indeed, you can check the same thing. So that is a nice little feature, and it's kind of reminiscent of real numbers, because when we talk about real numbers, we don't have inverses, but we have reciprocals, right? The reciprocal for a real number, and that's basically what's going on when we talk about the inverse of a diagonal matrix. Some other things with diagonal matrices, if I compute powers, remember we can do powers of square matrices. What would D squared be for this square matrix? Well, that means we multiply the matrix by itself. And when I do that, a 2 by 2 times a 2 by 2, of course, gives me a 2 by 2. First row dotted with this first column, 5 times 5 is 25. I'm going to write as 5 squared, which is 25, plus 0. 5 0 times 0 2 is 0. 0 2 times 5 0 is 0. And 0 2 times 0 2 is 2 squared, or 4. But you see the pattern now. So in other words, to take powers of, in general, any diagonal matrix, d to the k is just going to be take those diagonal entries and raise them to the kth power. That's all we do. We don't have to do all the multiplications. Everything off the main diagonal remains 0. So a diagonal matrix to any power is a diagonal matrix, and we just take the individual diagonal entries and raise them to that power. And then similarly, if we look at products of two diagonal matrices of the same size, like in this case, again, first row times first column gives me 4 times 2 plus 0. First row times second column gives me 0. Second row times first column gives me 0. Second row times second column gives me 3 times 5. Right? Of course, I get 8. 0, 0, 15 is what I get, but what I did in the intermediate helps you to see when I'm multiplying diagonal matrices together, we're simply, you can think of it as multiplying corresponding entries. 4 times 2 is 8, 0 times 0 is 0, 0 times 0 is 0, 3 times 5 is 15. And so remember when we defined matrix multiplication, it was not that, but it is essentially that when we're talking about diagonal matrices. And because that, if I'm multiplying two diagonal matrices, right, we just multiply their diagonal entries, and there's our answer. But notice, since real numbers we can commute, right, d1 times e1 is the same as e1 d1. That means if a and b are both diagonal, then they indeed commute, rather. AB is equal to BA. So remember, in general, that was not the case, right? For general matrices, AB is not necessarily equal to BA. But it is true if both A and B are diagonal matrices of the same size. So diagonal matrices have a lot of nice properties, and so very easy to deal with the arithmetic, if you will, of matrices if they are diagonal. We look also now at two more definitions, two new types of special matrices. Square matrix where all the entries above the main diagonal are 0 is called a lower triangular, and a square matrix in which all the entries below the main diagonal are 0 is called an upper triangular matrix. And so, above, we call it lower. Why is that? Well, because if I look at all the entries above the main diagonal, right, that's up here, we're saying, they're all 0. That means the things that are potentially non-zero are down here on the main diagonal below. So lower, see, we got this lower triangular. The idea is that. Upper triangular, all the entries below the main diagonal is 0. So the non-zero stuff is essentially up here in the upper triangular region. Now, in general, if you're upper triangular, that means the non-zero entries are where I is less than j. Remember, I is the row number, j is the column number. So for instance, 1, 3, row is 1, column is 3, 1 is less than 3, so that's an entry in the upper region. Whereas down below, A3, 1, I is bigger than j, row number bigger than column number down here. So for lower triangular, notice lower triangular right here, the aij's is 0 if what I is less than j. I is less than j, meaning the values above the main diagonal are 0. For upper triangular, then aij has to be 0 if I is greater than j. And of course, we just put in there the definition we just had for diagonal matrices. Now, notice diagonal matrices automatically are both upper and lower triangular. So a diagonal matrix is both upper and lower triangular. In fact, when we talk about diagonal matrices, we sometimes classify them with what we call the triangular matrices. These are all triangular matrices then, diagonal, upper, and lower triangular. A couple of facts that are fairly easy to think about. The transpose of a lower triangular matrix is upper triangular. Just think about that. If I do a transpose, remember a transpose is to swap the rows and columns. This row becomes the corresponding column, right, and so on. You can see how the lower triangular, if I transpose it, we'll get upper triangular, and vice versa. Transpose of upper triangular is also lower. It's going to be lower triangular. If I multiply a product of two lower triangular matrices, the result is going to be lower triangular. And if I multiply two upper triangular matrices, I get an upper triangular matrix. Okay. The product of lower triangular matrices or upper triangular matrices is not as easy as it is with diagonal matrices. But you can easily confirm that. Also, a triangular matrix is invertible if and only if, by the way, I don't know if I've said this, if you ever see the IFF word, that means if and only if. That's the shorthand notation for that phrase. Its main diagonal entries are non-zero. The if and only if means if we have a triangular matrix that's invertible, then its diagonal entries are non-zero. It also means if I have a square matrix whose diagonal entries are non-zero, and of course it's a triangular matrix, then it's going to be invertible. Okay, so it's important it has to be a triangular matrix for this if and only if statement to work. But that's very similar to, of course, diagonal matrices. So for all our triangular matrices, upper, lower, diagonal, they're going to be invertible if the main diagonal entries are non-zero. And if we have an invertible lower triangular matrix, its inverse is going to be lower triangular. And the inverse of an invertible upper triangular matrix is going to be upper triangular. So just as a review, here I have two matrices. So notice A is a lower triangular matrix because everything above the main diagonal is 0. And same thing for B. These are both lower triangular matrices. Which of these matrices is invertible? Based on what we talked about, which one is invertible? The answer is A. And the reason why? Well, since what? No diagonal entry is 0. No main diagonal entry, I should say, is 0. All right, here's the main diagonal. Here we have a main diagonal entry is 0, which tells me this matrix is singular, non-invertible. Is the product AB upper or lower triangular? Well, since A and B are both lower triangular, we just talked about this up here. The product of lower triangular matrices is lower triangular. So this will be lower triangular. Is A transpose upper or lower triangular? Since A is lower, its transpose will be indeed upper. We talked about that. And we know A is invertible. Is A inverse upper or lower triangular? No. Inverse of an invertible lower triangular matrix is lower triangular. Okay. So these are easy facts. You can prove it's pretty clear, but just think about some examples and you can see that's the case. Okay, one more type of matrix and we'll be done with these special matrices, and that is symmetric matrices. Again, notice this is a square matrix, so all our special matrices here are square matrices. A square matrix A is said to be symmetric if A is equal to A transpose, or if, of course, A transpose equals A. Sometimes you think of it that way, same thing. But remember, the transpose is where we swap those I and J, right, the rows with the columns. And so notice if A has entries Aij, this is going to be symmetric matrix if only if what? Aij is equal to let me say it again. Aij is equal to Aji. So swapping rows and columns does not matter. Here's an example. Look at this matrix A. What's its transpose? So the first row becomes the first column. Right? Second row becomes the second column. Third row becomes the third column. And if we take a look at this and compare the matrices, hey, lo and behold, they are the same. Right? So why are they called symmetric? Well, do you see the symmetry? Let me sort of rotate this around just a little bit here. Here's the main diagonal in A. I'm just going to sort of do a dashed line through that. But look at across the main diagonal, right? This is A 1, 2 here, which is 4, first row, second column, is equal to A 2, 1, which is second row, first column. And same thing here, first row, third column is the same as third row, first column. And second row, third column is the same as third row, second column. The symmetry is with respect to that main diagonal. The entries along the main diagonal could be anything. Right? It doesn't matter. They'll reappear after the transpose right along there. But in order for us to be symmetric, that has to be the case. Just some properties with symmetric matrices, because we will use later on. If A and B are both n by n symmetric matrices and K is any scalar, then A transpose is symmetric, A minus B and A plus B are symmetric, and the scalar multiple Ka is symmetric. And I'm going to prove these. It's real easy to prove, in theory, how to prove something is symmetric, and that is to simply use the definition. Take the transpose of the matrix and show that you get back to the original matrix. Okay? So number one, I look at A transpose. It's supposed to be symmetric, so let's take the transpose of that. And I need to get back to A transpose. Now notice that the premise is that A and B are both symmetric matrices. And so, of course, from this we know that A transpose is A and B transpose is B. Okay? But what happens when I take A transpose and transpose again? I get back to the matrix A. But A, since A is symmetric, is A transpose. And there's the proof. Simple as that, right? A transpose is here. I take the transpose of it, and what do I get back? A transpose. That's what symmetric means. Take the transpose. If you get back to the original matrix, it is symmetric. I'm going to prove A plus B transpose, or A plus B is symmetric. I take the transpose of A plus B. You remember from the property of transposes, we proved that this, or stated this was true, that this is A transpose plus B transpose. In other words, I can interchange. I can add the matrices and then transpose, or I can transpose and then add the results. But A transpose is A plus B transpose is B. And then lastly, in part 3, if I look at Ka, take its transpose, well, Ka all transpose is the same as K times A transpose. Again, this is something we stated in a theorem when we first introduced the transpose. So I can do the scalar multiple and then transpose, or I can transpose and then multiply by the scalar. But A transpose is A, and so I get back to Ka, and indeed this is true. So if a matrix A and B are symmetric, A transpose is symmetric, A minus B, A plus B is symmetric, and Ka is symmetric. Now, what about A times B, right? They're both n by n, so I can multiply them. If they're both symmetric, is their product going to be symmetric? Not necessarily. So I look at A, B transpose. Remember what that is? That is B transpose times A transpose. Right, this is from the properties of transpose. We proved this. B transpose is B, A transpose is A. But remember, BA is not necessarily equal to AB because we cannot commute, in general, matrix multiplication. So if two matrices are both symmetric, their product is not necessarily symmetric. If A is symmetric and invertible, then its inverse is symmetric, since what? A inverse transpose, you remember, is the same as A transpose inverse, but A transpose, since A is symmetric, is the same as A, and so we get the proof. A inverse transpose is A inverse. And then I just close with this for you guys. A square matrix A is skew symmetric if A transpose is equal to negative A, negative 1 times A. That's interesting. It's called skew symmetric if A transpose is equal to negative 1 times A. So my challenge to you is to find a 3 by 3 non-zero skew symmetric matrix. The zero matrix indeed is going to be skew symmetric. But find a 3 by 3 matrix that where not all entries are 0, right? Find such a 3 by 3 skew symmetric matrix. So see if you can do that. You can send your result to me by email or something like that. That would be great. Don't just Google and look it up. Try and think about it and figure it out on your own. See if you can do that.